What I'd like to talk about is maybe some practical applications of some of the voodoo, some of the magic, and how that applies to modern embedded and rugged systems. So I'm taking a look at aspects of GPGPUs. They've been around for a while, but now they're starting to get traction and they're starting to get really used in today's environment and in today's applications. So what are some of the aspects of what the needs are? Why use the GPU? I mean, you've heard a lot about it. What's so special about it? What makes it important? What's this concept of deep learning and neural networks? I did put in WTH in there, so just so that you see what I really meant. And then current implementations of just exactly how these things are being used. This is the no-duh slide, which is what's going on in the industry and why is it important, is that the number of display panels used in today's applications is just growing exponentially. It's every time I turn around, the old steam gauges are being replaced by modern flat panel displays. The camera resolutions and the panels themselves are getting much, much larger, and the resolution on those is growing also exponentially. And so what's really going to be the next growth area is that the number of pixels in the panels and the number of pixels in the cameras and the sensors is growing. And the sensors that are out there are just unbelievable. It's not just your cameras anymore. It's LiDAR, it's radar, it's gamma ray detectors in large planar, 2D planar arrays that are being used. And I'll talk a little bit later about how they're being used. So some of the aspects and some of those applications are in flat panels. They're all over today's aircraft, modern aircraft. They're all over the Orion capsule, which is the next generation spaceflight capsule for lunar and Mars and beyond exploration. And believe me, challenging, very challenging. Rugged displays or LCD displays don't like working in wide extremes of temperature. So what's going on with imaging? Let's look at one aspect of how these things are, how these are being presented. I tried to show you a couple of pictures here of what happens when objects are partially obscured and how do you wind up doing some object detection and threat assessment and classification and targeting of those images. You can see down in the lower left, there is a guy actually hiding in the hills of Afghanistan. If that circle wasn't around it, promise you wouldn't see it. You wouldn't see him. So there's obviously purposeful and hidden methodologies of obscuring a target or obscuring yourself. And then there's also unintentional, which is people walking in front of displays and what have you. So there are also aspects associated with the electronics themselves and the technologies. There's environmental factors associated with imaging, where you have fog, dust, rain that can obscure the image. And there's also adverse lighting conditions. That happens all the time, so whether do you have a LiDAR or a infrared backup to the camera. And then there's things like artifacts, which are sun reflection, sun flare, lens bloom. I mean, we've all seen the cameras in Hollywood as they wipe across a scene that has lights like these in it, and all of a sudden 5 or 6 blooms walk in front of the image. These are all part of the compound lenses that are part of the system for focus. So many times in auto target recognition or auto recognition themselves of systems that are remotely located, you're going to have obstructions and or purposeful hidden aspects that are trying to keep you from being identified, and they won't classify correctly. So what's going on here, and how do we address that? So in terms of where the pitfalls are, and this is some of the things we've seen in our experiences with our customers, is that there's so much data that the CPUs are getting starved. There's just so much data, and it's running at such a high rate because of the high pixel rates that the CPUs that are out there aren't keeping up. So there's limited computing power that's associated with that. So what customers are doing are actually dumbing down their sensors. They're either pulling back the throughput on the sensors, or they're making the sensors smaller to keep up with the compute element. That seems silly to me, but that's what's happening. So those limitations will slow the response and slow the real-time response. So do you really need to make those compromises? All right, so what's really the factor here is that you've got CPUs like the Intel products, the PowerPC products, multi-core products that are they're great. And they are fast, and they've got acceleration engines. They've got several cores in them. They've got all the control elements, the RAM, et cetera. But it's really a task-oriented machine. And it tends to be serial processing more than using sophisticated complex cores in tandem. What's happening now with the GPGPU is you can see quite readily just what's exactly going on here is there's hundreds and hundreds of cores that are there that are essentially, each one of those are a CPU themselves. They can be used to run algorithms, and there's many different ways that you can apply these algorithms either in serial or in parallel to process the data. So you can see that the parallel processing is the way to go. And they're simple cores, but there's lots of them. And you can apply that to the application. Think a long time ago when displays were pretty small and you try to draw a diagonal line on the screen. What would you see? You'd see these little stair steps of a line, and people hated those. So how did you address the issue? How do you fix the issue? Is that you wind up taking some of the pixels that are actually next to the lines, next to the stair step, and you blur them. And wind up blurring them is you wind up straightening out the line. So it's a method of anti-aliasing. So the algorithms to do that are pretty straightforward, but it chews up CPU time to do that, so that's where the GPU came from. Let's do that automatically, let's do that in the background, so let's get nice, crisp, sharp displays, and let's move on. So now in the GPGPU market, there's open source called CUDA, which is Compute Unified Device Architecture, in case I had to look that up about 12 times because I keep forgetting it. Older. So there are a lot of open source libraries out there, a lot of toolkits, a lot of tool chains to allow you to build your algorithms up, and a lot of that hard work of designing these systems using lots of parallel cores together have been already worked out. And there's reference platforms and reference materials and reference code. It's all open. It's all there for you to use. Where's GPGPU showing up? My goodness, it's just about everywhere. Cars, especially vehicles, track vehicles, wheeled vehicles, you name it, it's showing up everywhere. And the more and more panels that are being put into the systems, getting rid of, as I said, the steam gauges, the more pervasive it is because it gives the designers much more flexibility in how they design the system, and as well as being able to implement the feedback from their focus groups instantaneously. If they don't like the gauge placement, they don't like the way the gauge looks, heartbeat, you can change it. So a lot of that's happening now. So it's the complexity of design, and the implementations are moving much quicker, and the GPUs are doing a lot of the heavy lifting in terms of getting the displays. And trust me, there are more and more displays showing up in these vehicles every day. So here's one vehicle. It's probably the world's best military vehicle that's ever been created, the M1H64 Combo. This thing kicks ass. It's just unbelievable. A little on the heavy side, but okay. It's showing up in defense applications as well. More and more that we work with our customers, it was just a display, situational display. Now it's tactical displays, and now it's the entire aircraft are all on flat panel displays. There's not a steam gauge at all in some of the new modern helicopters. So it's coming. So what the heck is deep learning and neural networks? The human brain is an unbelievable compute engine. And how does it really work? Is the synapses and neurons all work in parallel in order for you to recognize objects. And you learn it from a small child as you grow up, and I'm telling you nothing you don't already know. However, the idea is to get the machine to do the exact same thing. And along with that is also the learning machine, the machine that self-adapts and self-learns. And that's happening now. These neural networks that are being put in place into UAV platforms and vehicles, it's absolutely amazing. They're taking these GPGPUs, which are great for visual, for graphics outputs, and for imaging, but they're DSP engines. That's absolutely what they are, digital signal processing, and they are doing the heavy lifting of understanding of what an image is, how to characterize it, how to identify it, and how to move forward. So what's happening is that the brain and the computing engine now model the environment through a continuous learning process. and it's increasing its intelligence over time. I know this sounds like Skynet, and actually, I'll be honest with you, there are people actually thinking about that, and actually thinking about Isaac Asimov's 3 laws, and making sure that those are implemented up front. So it's not science fiction anymore, it's science fact. So with some of the engines that are out there, NVIDIA being one, the CUDA model uses the deep learning process in order to make these systems more self-aware and be able to, being able to understand what their environment is and what they're actually seeing in imaging and whether they can identify that as a threat, friend, or foe. So looking at increased intelligence and looking at neurons and looking at all the way the synapses and the neurons work together and the way it's nothing but pattern recognition. That's really what your brain is doing, is very sophisticated pattern recognition. You look at an alphabet, you look at an alpha character, look at a number, you're able to tell what that is because your brain knows what it is because it's part of the synapse structure. So that's exactly what a multi-core GPGPU is. There's Perceptron. I know that sounds like a really nifty word. It's been around since the 1950s. In concept, it hasn't changed at all. You have a number of inputs. You have a number of weighting factors that go with those inputs, which are variables, which are coefficients, essentially, and those are input into an algorithm, whether the algorithm is a summing algorithm, differentiating algorithm, whatever that algorithm happens to be, and it has an output. Now, this is a very simple model. What the more complex model is that the output of that perceptron feeds back and starts changing some of the weighting factors. And what those changing of the weighting factors is how it learns. So, in an example, you have a multi-layered neural network model. It's consisting of lots of parallel processors and perceptron-like nodes looking at an object. So you have an image of a car. Obviously, it's not a submarine, but the computer doesn't know that. So how does it go through the process of understanding what the heck that thing is? So it looks at the image and then starts parsing the image down and looking for lines. It starts looking for patterns, known patterns, triangles, circles, whatever the applications program is put into the system, into the machine, and it starts working down through the process of saying, once I have these patterns put together, how can I rearrange those patterns such that it starts generating something that looks like I think I know what it might be? So as it starts whittling down through the process, it then comes to the end, and it starts learning that this is a car, it's not a truck, it's not a jet, it's not a whatever, and then it finally comes to the end and says, okay, that's an Audi. There are ways to implement these things. This is something a little different that we brought to the market. Where's the horn? Okay. Our customers are asking us are asking for us of ways to take this rugged GPGPU and put it into real-world systems, creating a neural network of systems, interconnected systems through Ethernet switches, such that they can create their own neural networks and pass data through many different types of sensors and do sensor fusion, and they want it on a nice, small, rugged, compact form factor. This is one example of an NVIDIA Jetson with 256 cores tucked into a nice little rugged box. It's about 5 by 5 by 1. And this can go anywhere on an aircraft or in a vehicle, and it takes up almost no room, and it provides you a teraflop of processing power, or was it 66 gigaflops per watt. Megaflops. Gigaflops, I'm sorry, it's gigaflops per watt, yes. So from a teraflop. So it's very low power, and it's a lot of processing power, and it's self-learning.